I'll start recording. Okay, so this week we're going to talk about probability and probability distributions. So nothing in life is certain, and everything we do, we gauge the chances of successful outcomes from business, which is why you're taking business statistics, to medicine, what's the probability of some treatment working, or weather, which is the best job in the world because meteorologists get to be wrong all the time. But for most of human history, probability, the formal study of the laws of chance, was used primarily for gambling. So nobody really knows the inception of when gambling began, but we know it goes back to at least ancient Egypt, where sporting men and women used four-sided astragali made from animal heel bones. So kind of like a four-sided dice, which is pretty important to our underlying concepts of probability, but we'll get more into the use of dice and explaining the odds of something happening. So we had a Roman emperor, Claudius, 10 BCE to 54 CE, who wrote the first known treatise on gambling. Unfortunately, this book was How to Win at Dice was lost, probably during the fire in the library at Alexandria. But rule 1, let Caesar win 4 out of 5. Modern dice, though, grew popular in the Middle Ages in the time for a Renaissance rake, a Chevalier de Mer, to pose a mathematical puzzle. So he said, what's likelier, rolling at least 1 6 in 4 throws of a single die, or rolling at least 1 double 6 or 2 6s in 24 throws of a pair of dice? So the Chevalier reasoned that the average number of successful rolls was the same for both gambles. Chance of 1 6 equals 1 6. The average number in 4 rolls equals 4 times that 1 6 probability is 2/3. So the chance of a double 6 in one roll, so 2 6s out of 36 possible combinations, is 1 out of 36. So the average number in 24 rolls should be the same, right? 24 times 136 equals 2/3. What he wanted to know is why, when he was playing, craps, which is the 2 dice game, I assume that it was modeled off of, why did he lose so much? So de Mer put the question to his friend, a very famous mathematician, Blaise Pascal. He said, at last, a problem that turns me on. Although Pascal had earlier given up mathematics as a form of sexual indulgence, he agreed to tackle de Mer's problem. So Pascal wrote his fellow genius, Pierre de Fermat, and within a few letters, the two had worked out the theory of probability in its modern form, except minus all these cartoons. So he said, dear Pierre, what a beautiful theory we could have if only one of us could draw. So this chapter and the next chapter is still going to be a lot of definitions and kind of like underlying base knowledge before we get into how can we actually use statistics to solve business problems. But we need to cover some terminology first. So these basic definitions, as our gamblers play out their games, observe an outcome, which we'll talk about, as well as the use of random experiments. So a random experiment is the process of observing the outcome of a chance event. So elementary outcomes are all possible results of the random experiment. And the sample space is the set or collection of all those elementary outcomes. So just some kind of key terms that may pop up. So if the event was a coin toss, so in a coin toss, we can have heads or tails. The random experiment consists of recording its outcome. So you flip a coin, you get a head, you mark 1. Flip a coin, again, you mark tails, you mark. So that's the outcomes. So elementary or possible outcomes are either heads or tails. So there's 2 possible outcomes. And the sample space is the set written with these little curly braces here. So when we look at dice in a second, I think, you'll see, well, it'll probably be on the next slide, but you'll see these curly braces with all the possible outcomes in that set. So if we were using just 1 die and we were to roll it, there's 6 possible sides to that die. So the sample space of the throw of a single die is a little bigger. So it's 1, 2, 3, 4, 5, and 6. And for a pair of dice, the sample space looks like this. I make one die white and one black to tell them apart. But so there's 24 combinations, right? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 6 by 6. 36. So 36 combinations. That's what I was getting at. Okay. So I want you to remember these combinations because we're going to refer back to this kind of mental image of what all the combinations are for a pair of dice being thrown. So now let's imagine a random experiment with n elementary outcomes. We have the first, second, all the way to x or whatever. So we want to assign a numerical weight or probability to each of those outcomes, which measures the likelihood of it occurring. So we write that as the probability of O of I, or P with whatever variable of interest in the parentheses. So a lot of times we'll see, P of A or P of B, and we'll get some more advanced kind of notation in a second. So for example, in a fair coin toss, heads and tails are equally likely, and we assign them both the probability of 0.5. Because, in a fair coin, it should be land on heads or tails each half of the time, so 0.5. So the probability of heads is equal to the probability of tails, which is equal to 0.5. So each outcome comes up half the time, such as in any sports coin toss before a game starts. So in the roll of 2 dice, there are 36 elementary outcomes, all equally likely. So the probability of each is 1 out of 36. So for instance, the probability that the black die is 5 and the white die is 2 is equal to 1 over 36. So which means if you rolled the dice a very large number of times, in the long run, this outcome would occur 1 out of 36 of the time. So that's kind of a concept of the law of large numbers, and we'll come back to that theory probably in a little bit. So what if our gambler cheats and throws a loaded die for the sake of argument, so as that now a 1 comes up 25% of the time in the long run? Sample space is the same as for a fair die. So we have, our sample space is 1, 2, 3, 4, 5, 6. And that's the set of possible outcomes. However, now we've adjusted the likelihood of rolling a 1 to 0.25. So that probability is slightly higher. But the probabilities are different, right? So now P1 equals 0.25, and the remaining probabilities all add up to 0.75 because all probabilities have to add up. So if 2, 3, 4, 5, and 6 were all equally likely, then each one would have probability of 0.15, or 1/5 times 0.75. So that's how we got the remainder of what the other die probabilities would be. So the probability of perception is 20%. Probability of a walk is 5%. Probably because he's too busy paying attention to this TV to pay attention to his dog. I recently just got a puppy, so I guess I could see how this could happen. Anyhow, so now what can we say about the probabilities of O in an arbitrary random experiment? So first of all, what is the probability of our outcome of interest being greater than equal to 0? So Chevalier says worse than impossible isn't possible. Right, so what does this mean? Probabilities are never negative. Probability of 0 means an event can't happen. So less than 0 would be meaningless. So that's why, you can't have a fraction over 0. Same underlying concept in math. So second, if an event is certain to happen, we assign it a probability of 1. So in the long run, that's the proportion of times it will occur. In particular, the total probability of the sample space must be 1. If we do the experiment, something is bound to happen. So basically, all probabilities have to sum up to 1, and none of them can be negative. So put those two together, and that's the characteristics of properties of probability. Non-negative, and all outcomes must add up to 1. So let's do an example. So an experiment results in one of the sample points, E1, E2, E3, E4, E5. So we have 5 sample points or parts of this experiment, and we're given a set of probabilities, but we want to find out what's the probability of that third experiment. So we know the probability of E1 is 0.2, the probability of E2 is equal to 0.1, the probability of E4 equals 0.2, probability of E5 equals 0.2. So I've uploaded a kind of work along spreadsheet if you'd like to download it, but basically it just has all the data that I'll talk about in certain example problems. So based on those laws of probability, how could we solve this problem where this particular value is of interest? Well, we know that it sums to 1, right? So we could find out what the other probabilities sum up to and then subtract that from 1, basically finding the complement of that. So if we use sum formula for this value, all the other probabilities add up to 0.7. So if we want to know what this probability should be, it should be equal to 1 minus the remainder of the other probabilities, 0.3. It's a pretty simple way to prove the laws of probability. So an event is a set of elementary outcomes. The probability of an event is the sum of the probabilities of the elementary outcomes in that set. So for instance, some events in the life of a 2-diced roller are dice add to 3. So there are 2 different combinations that can give you a 3, right? You can roll a 1 and a 2 if you had, the white die and the black die, or you could roll a 2 and a 1. So there's 2 possible ways to roll dice that add up to 3. Dice that add to 6, well, now you have several more combinations. 5 to be exact. The 3, or any doubles can only count as 1 because, so that's going to kind of limit some of our probability. So what are the odds that the white die shows a 1? Well, then you need to look at all possible combinations where the first die is a 1, and then the second die or the black die could be a 1, 2, 3, 4, 5, or 6. So that provides 6 out of 36 possibilities. So if we go back up, you could actually count these out if you didn't put them, if you didn't have this column of data. So likewise, the black die shows 1. You'd have 1 out of 1, or basically the second die will always be a 1, so it's going to be 6 combinations as well. So example 2. In this particular example, we need to find several different probabilities. So to solve this problem, I've copied them, the little plot here. So first we need to determine what's the probability in this little Venn diagram of A. So we have this circle that's A, and we denote how many points are in that circle out of all 10 points. So in our particular example here, we have 10 total points, right? And 3 of those points are in the circle given to A. So 3 divided by 10, because probabilities are like ratios, right? So 3/10. Now, similarly, in this circle of B, we have 2 points, right? So it would be 2 divided by 10, or 0.2, or 20% probability. So now, let's say these points have different weights. And this, we assume they were all equally likely, right? So each point was worth a tenth. But what if we adjust them to where points 2, 5, 8, 9, and 10 are all equal to 1/20th, and points 1, 3, 4, 6, and 7 are all equal to 3/20ths? How would we solve for A and B at this point? Well, we have to denote what each of them are, right? So we know that 2 is 1/20th, 8 is 1/20th, but 7 is 3/20th. So we have, so I can denote this. We know that 2 and 8 are both 1. So we have, 1, 1, and 7 was 3. Think of it as 5 total in A, divided by 20. So 25% probability based on this uneven weight. And as for B, what's the probability of it being B with these new weights? Well, we can see that 1 is 3, 7 is 3, which is going to sum up to 6. So now we have 6 out of 20 is, I can get this done. No, anyhow, so that's how you, in a second we're going to look at finding the other possible ways that you could find the values for different ones. We're going to talk about an intersection, which will only be where, in a Venn diagram, they both, the point is in both circles. They can find ways to get the union, which we're going to talk about, and or find other probabilities based on how they are arranged. So the beauty of using events rather than elementary outcomes is that we can combine events to make other events using logical operators. So the relevant words are and, or not. If you know anything about electrical engineering or integrated circuits, this draws back onto binary logic, but we're going to learn how they really represent in statistics. So that given, we're given two events, E and F, and we can make new events. So we can determine what is E and F, the event that E and the event F both occur. We have E or F, the event E or the event F occurs, or both do. So basically everything in both circles. And so, and it has to occur in that middle part here. And not E, the event E does not occur, would be kind of, if we're trying to say event E, whatever does not occur in A in this example. So it would just be everything else. So basically it's called, another term is the complement. Okay, so let's return to the dice throwing example. If C is the event, white die equals 1, and D is the event, black die equals 1, then C or D is the entire shaded area. So it's kind of blurry, but it's bottom column and the far right column, or bottom row and the far right column. So C or D is the entire shaded area where one die or the other is 1. C and D is where the shaded areas overlap. Both dice are 1. So in an OR statement, at least one of the die has a 1, right? But using the word and, both of them would have to have a 1. So this illustrates the addition rule for any event E and F. So what is the probability of E or F? Is the probability of E plus the probability of F minus the probability of E and F. So adding the probability of E and the probability of F double counts the elementary outcomes shared by E and F. So we have to subtract that extra amount, which is why we have to add this last little statement here, which is the probability of E and F. So the probability of C or D equals 11 over 36. As you can see by counting elementary outcomes, likewise, the probability of C and D was 1 out of 36, which was when you rolled snake eyes, or both 1s. So we can confirm the formula by putting all the probabilities in. So we have 6 out of 36, 6 out of 36, so that's the bottom row in the right column, minus 1 out of 36, which is the one instance where we had snake eyes are 2 1s. So it would be 12 out of 36 minus 1, which gives us the 11 out of 36. That's how we define the conditional probability P, C, or D. But sometimes the overlap E and F is empty, and the two events have no elementary outcomes in common. In that case, we say E and F are mutually exclusive, making P and F equal 0. Where we see the mutually exclusive events, A, the dice add to 3, and B, the dice add to 6. So there's no overlap between these two shaded diagonal regions. So for mutually exclusive events, we get a special addition rule. If E and F are mutually exclusive, then P, E, or F equal P of E plus P of F. And we can check that with this basic probability down here. So we have 2 combinations plus 5 combinations out of 36, so 7 out of 36. And we don't subtract anything because there's no overlap in their probabilities. Finally, the subtraction rule. For any event E, the probability of E equals 1 minus P not E. So this is useful when P not E is easier to compute than P of E. For instance, let E be the event A double, so 2 1s, is not thrown. So the event not E, A double minus 1, is thrown, has the probability of P not E equals 136. So P not E would be 35 out of 36. That's called the complement, or the other part of a probability. So let's do another example. The sample space for an experiment contains 5 sample points with probabilities as shown in the table below. Find the probability of each of the following events. So either 1, 2, or 3, either 1, 3, or 5 does not occur. So should be able to do that here. So since we're only rolling 1 dice, what does that mean? Since we're only rolling 1 die, we're not going to have to subtract anything. So it's just going to be the sum of the possibilities of these events occurring. So it would be equal to the probability of 1 plus the probability of 2 plus probability of 3. So in this example, 48% chance that that would occur. Now, what's the probability of B? You can do it the same way. Basically, what's the probability of it being odd given these particular probabilities? So equals 1 plus 3 plus 5. So 52%. Finally, what is the probability that 5 does not occur? So basically we're saying not 5. Well, we know that all probabilities have to add to 1, so we can just say what is the probability of not 5, or the complement of 5 is 1 minus whatever the probability of 5 is. So probability of C is 77%. based on this particular example. So, in example 4, in a survey, 4,155 nannies were placed in a job in a year. Only 35 of those nannies placed were men. So find the probability that a randomly selected nanny who was placed during the year is a male nanny. So how do we do that? So pretty basic. It's just a ratio. I didn't even put a separate tab here. So we just want to know the ratio of a randomly selected nanny being male. So we know only 35 of those nannies were men. So it's just 35 divided by the total. So 0.008. So less than 1% chance that a male nanny is going to show up to your house. Example 5. So uses the combinations rule. So we'll talk a little bit about that. So particular formula, if you see this kind of funny setup where you have, it almost looks like a fraction, but it's missing the little division bar. But the combinations rule comes with a particular special formula. So this basically says you have a sample size of 9 with 5 combinations. So C, we're looking for combinations of N, R. We're going to use something called factorial, which is why I thought this would be a good example, because you can learn how to use another Excel function. We want to implement this function. So we can write it out. Well, so we know that N and R, so N is equal to 9 and R is equal to 5. Double check here. Don't talk about it right here. So in factorial, we'll do equals factorial. Fact returns the factorial of a number equal to 1 times 2 times 3 times all the way up to the number. So 9 factorial is 1 times 2 times 3 times 4 times 5 times 6 times 7 times 8 times 9. That's all the factorial is. So we know that 9 factorial, that's the numerator in our particular combinations function. And then we want the factorial of N minus R. So N minus R. And we want R factorial as the last. Okay, so that gives us those values. So this is N factorial and R factorial and R factorial. So now let's put those values into the formula. So we want this value divided by this value times 126 combinations. Now that you've figured this formula out, if you had a different set that you had to do your combinations rule on, you should just be able to change this number. Now you've created a little calculator that will give you the total combinations. May become helpful in your homework. Okay, so back to learning about conditional probability. As I was saying, one version of the book says, you have or and not. And then the other terms you can use are intersection, which is like A and B, so it has to be a part of both. A union, A, kind of a U, B, which is everything that is in both spaces. You have the complement of A, or A naught, which is everything that's not in A. And then, of course, something that's mutually exclusive or disjoint, which was the case where we said these two probabilities don't have any overlap when calculating them out. So, rules of complement, kind of touched on this a second ago. Probability of A complement is equal to 1 minus the probability of A. So it makes it a little easier than trying to add up all the probabilities of something when you can just subtract one from it and you can get its complement. So when we talk about the union, or A or B, to find that probability, we would need the probability of A plus the probability of B minus the probability of A and B, or the intersection of A and B. So given this particular formula, we just have to solve for whatever this value is of interest, so we're interested in the intersection, or given the union and the two probabilities of A and B. So look at an example. Suppose we have the probability for B, probability for D, and we also have the probability of the intersection of B and D. So let's find the probabilities below. So in the first example, we want to find probability of the complement of D. So that's the other part that's not included in D, right? So A should be pretty easy. It should just be equal to 1 minus probability of D. It should be 0.4. For part B, we want to know what is the probability of the complement of B. So it should just be 1 minus the probability of B. 7. So part C wants to know what is the probability of the union. So we just set up above what the union was, right? It's equal to the probability of A plus the probability of B minus the probability of the intersection. So we're given the probability of B and D in the intersection, so it should just be probability of B plus the probability of D minus the probability of their intersection, or where they overlap, and that will give us the union of probabilities B and D, or the union, probability of the B union D. All right, so that covers the first little under set of probability, but we'll continue on. So the formulas we just derived are all in fact adequate for answering Damir's question, but not easily. You might try using them on a simpler question. What's the probability of rolling at least 1 6 in 2 rolls of a single die? We need more machinery. So we're going to introduce something called conditional probability, an essential concept in statistics. So talk a little bit more. So suppose that we alter our experiment slightly and throw the white die before the black die. What's the probability that the faces sum to 3? So before the dice are thrown, the probability of A is equal to 2 out of 36. Now suppose the white die comes up 1, event C. What's the probability of it now? Now we have slightly more information than we did in the previous version of this problem, because before we were interested in, rolling a 3 where the white die or the black die could be a 1 or a 2 and give us a 3. So there was 2 possibilities, right? The white die 1, black die 3, and the white die 3, the black die 1. But now we've rolled a 1 So there's only one possibility for the black die to be, for it to be rolled as a 2, so it'll add up to 3. And so that kind of alters our probability. So it becomes a condition. We call it conditional probability that that event will occur. Given the condition that event C has already occurred, we write P of A given C. That's how you read this vertical bar. So it's probability of A given C. So before any dice were thrown, the sample space had 36 outcomes. But now that the event C has occurred, the outcome must belong to the reduced sample space C. So now there's only one combination that will give us our desired outcome. So in the reduced sample space of 6 element outcomes, only one outcome, 1, 2, sums to 3. So the conditional probability is now only 1/6. So in general, to find the conditional probability of P of E given F, we look at the event E and F as part of the reduced sample space F. So we translate this into a formal definition. The conditional probability of E given F is the probability of E and F, so the intersection of E and F divided by the probability of F, which you can directly verify some intuitive facts. Probability of E given E equals 1. Once E occurs, it is certain, right? It's already happened. When E and F are mutually exclusive, the probability of E given F equals 0. So once F has occurred and we know E can't occur, then it must equal 0. So with the dice, the probability of A and C is 1 divided by 36 divided by the probability of C, which was 1/6. So you factor that out and you get 1/6. Rearranging the definition gives us the multiplication rule. So P, E, and F is equal to P, E given F times the probability of F. So what we would like to reduce to a special multiplication rule under the favorable circumstances that the probability of E given F equals probability of E. That would be excellent. And while we're waiting for the next page, note that swapping E and F proves that probability of F times the probability of E given F is equal to the probability of E times the probability of F given E. So you can swap those around and they should give you an equivalent answer. So independence and the special multiplication rule. So two events, E and F, are independent of each other if the occurrence of one has no influence on the probability of the other. So for instance, the roll of one die has no effect on the roll of another unless they're glued together magnetically. So unless we're cheating somehow. So in terms of conditional probability, this amounts to saying that the probability of E is equal to probability of E given F, or equivalently, probability of F equals the probability of F given E when E and F are independent. And we get a special multiplication rule that probability of E and F, or the intersection, is just equal to the probability of E times the probability of F, but only under this special rule. So let's verify the independence of dice using these formulas. So C is the event white die comes up 1. D is the event black die comes up 1. And we have probability of C given D is equal to the intersection of C and D divided by the probability of D, which we had put on the previous page. So 1 out of 36 divided by 1/6. So you multiply by the reciprocal and you get 6 times 1, 36 times 1, and then you reduce the fraction, you get 1/6 is equal to the probability of C. The white die show 1 obviously does affect the chance that the sum of the two dice is 3. Probability of A given C, in this case we had a particular probability. So this formula doesn't hold up, right? So the probability of A was 1 over 18, and it's not the equivalent. So these two events are not independent because there was more than one possible outcome for the original goal. So before going on, let's summarize all the rules that we've talked about up to this point. We had the addition rule. So what is the probability of E or F? So that's the probability, or the union, equals the probability of E plus the probability of F minus, where the intersect, or where those two probabilities would overlap. There's a special addition rule when E and F are mutually exclusive, where it's the probability of E or F equals probability of E plus the probability of F. The subtraction rule, which is also just called the complement, is probability of E equals 1 minus probability of not E. Multiplication rule, probability of E and F is the probability of E given F times the probability of F. Finally, special multiplication rule, when E and F are independent, probability of E and F equals the probability of E times the probability of F. Might be good to refer back to this page when you're doing your homework. So, kind of what we were just talking about, and different terminology depending on which book you're using. Probability of A given B is equal to the probability of A and B, the intersection, divided by the probability of B. So we have two events, A and B, and we have the probability of A and the probability of B. For the probability of A given B, we need to find the intersection and probability of B given A. Let's see if I have that. Okay, so if we want to find the intersection of A and B with the available information we have, let's go back. So we're interested in the intersection of P and P of E and F, right? So P of A and B. So we know that the probability of E given F, probability of A given B, in this case, times the probability of F. Find A, we're going to use that rule. We have the probability of A given B, 0.5. We're going to multiply that by the probability of B, right? So just the multiplication rule. So that will give us the intersection. If you think of that with the Venn diagram, that's going to give us, based on the special multiplication rule, the little section where both circles would touch, and only that part. Now, the second part is B, is to find the probability of B given A. Let's see. Given the intersection now of probability of A and D, then we need to divide that by the probability of A. So we divide this by the probability of A, give us the probability of B given A, based on rearranging the formula. Okay. So, chapter 4. Now we're going to talk about random variables and probability distributions. Okay, so we'll put the two together. We're going to look at, means and variance with respect to how they work with probabilities and the binomial distribution. So if we imagine a random experiment repeated many times, we expect that the actual outcomes over time will be governed by their probabilities. So the probabilities form a model for real-life experiments. So why not do for the model what we've already done for the data as it describes? So we're going to talk about two, number sets. So we have continuous variables. A set of data is said to be continuous if the values belonging to the set can take on any value within a finite or infinite interval. So all the numbers between 0 and 1 would be continuous. But if kind of on the other flip side of that, we have discrete numbers, which is a set of data said to be discrete if the values belong to the set are distinct and separate. So if we had like flipping a coin and we made heads 0 and tails 1, and we kept track of that, that would be discrete values because it could only take the value 0 or 1. Or same thing with the roll of the dice. Those would be discrete, right? Because it can be a 1, 2, 3, 4, 5, 6. It can't be 3.5 because it's not part of the set. But for a continuous variable, it would be some way to create a number anywhere between 1 through 6, including all decimals. So continuous variables are usually measured, and discrete variables are usually counted. So if they're countable, it's probably discrete. And if we have to take a special measurement, like weight or temperature, those would all be on a continuous scale. So if we look at height by age, age would be, in general, a discrete variable, right? You're either 1, 2, 10, 22. Hypothetically, you could be 22 and a half, but in general, we talk about age as a round number, right? Cost of tickets. So if you bought 1 ticket, 2 ticket, 3 ticket, so tickets would be discrete. Numbers of customers, you can't have half a customer, right? You'd have 1 customer, 2 customers, 3 customers, etc. Same thing with months. But you can look at some of these variables on a continuous scale as well, right? So what is the cost by pounds? So you have weight, different weights. Let's say you're buying tomatoes at the market, I don't know, and 1 tomato is 1.3 pounds. Well, you know there's a flat cost to that. It's $2 a pound or whatever. So you multiply the number of pounds that you weigh out or measure, and you multiply it by the cost, and it would give you a very linear line. But it could also be nonlinear, which I'm not sure we get that far in this class, but you know, you don't grow at a constant rate, right, of height as you get older. In fact, you know, as you get older, you actually start to get shorter in your later years. Temperature over time. I mean, if you think about, you know, how the temperature changes throughout the day, especially in Florida, you know, it's like, you know, 60 degrees at 6 o'clock in the morning, and then it's like 90 degrees by 4 o'clock, and then it drops back down to like 70 degrees by 10. You know, throughout the day, there's this continuously changing effect. So hopefully that provides some good examples of the difference between discrete and continuous variables. So the key idea is the random variable x, which we write as a large X. So a random variable is defined as the numerical outcome of a random experiment. So for example, imagine drawing 1 student at random from the student body. That's the random experiment. The student's height, weight, family income, SAT score, and grade point average, or GPA, are all numerical variables describing properties of that randomly selected student. But they're all random variables. So the administration's job is to turn students into statistics. Not JU, though. Another example would be to toss 2 coins, the random experiment, and record the number of heads, 0, 1, or 2. So 2 tails would be 0. If we got either heads and tails or tails and heads, it would count as a 1, or 2 heads would count as a 2. So note the notation. The variable is written with a capital X. The lowercase x represents a single value of x. For example, x equals 2 if heads comes up twice. Another example is based on the familiar toss of 2 dice. So let y represent the sum of the dots on the 2 dice. For this random variable y can be any number between 2 and 12. So what is the sum of the 2 dice being rolled? Now we want to look at the probabilities of the outcomes. For the probability that the random variable x has the value of x, we write the probability of x, big X equals little x, the actual, you know, x that we calculate out, or just the probability of x. For the coin flipping random variable x, we can make the table x for the above here. Basically, let's turn this into a table. So the probability of x equals x. So if it's 0, it's 1 out of 4, right? So there's 4 possible combinations where you get, what was it, 2 tails, right? Now to get at least 1 heads, there was 2 combinations. So 2 out of 4, which reduces to half. And to get 2 heads would be 1 out of 4. So this table is called the probability distribution of the random variable x. So for the random variable y, the sum of the 2 dice, the probability distribution looks like this. So the comic is of craps table, I think, or it looks like billiards, but that's why they say they're giving up dice, because you'll notice something very funny about these numbers. On the snake eyes and 2 6s to give you a 12, the probability is pretty slim, but in craps, 7 is the most common value, and so if you roll a 7, then you crap out, right? So the odds are not actually in your favor, but unless you bet on rolling a 7 and you get multiple rolls of 7, which is possible. I mean, it does have a high probability rate. I don't personally play craps though. So now let's draw graphs or histograms showing these probability distributions for each value of x. So we draw a bar equal in height to the probability of x. So the highest probability was 2 out of 4, right? Or 50%. And that was when we could draw or flip 2 coins and get either a heads and a tails or tails and a heads. So it's easy to see that the total area of these boxes is 1. Each box has base 1 and height p of x. So the total area is the sum of the probabilities of all outcomes. So we're not violating any laws of probability, right? But you also notice that at this very small scale, we have, it kind of starts to look like a bell curve, right? I mean, we only have a very small probability distribution, but you can see even from this point, it's starting to look kind of normal. However, we know that flipping a coin, there's only 2 possibilities, 0 and 1, right? So that comes from a binomial distribution. So how could something that comes from a binomial distribution begin to look like the normal distribution? Keep that in mind. So here's the probability histogram of the random variable y, showing the probability distribution of the sum of 2 dice. So we can see the highest probability is for the rolling a 7 because there's the most combinations, right? And then we have, the seems like there should be a bar here for 1, but it seems like it's off a little bit. Maybe it's shifted over. Doesn't matter. But what I want you to notice is just like with the dice, now we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 data points, and we can kind of see that even though we know this didn't come from a normal distribution either, it does start to become normal with each outcome that we would roll. So why do we call these graphs histograms? You'll recall that in chapter 2, a histogram was a graph that displayed how many data points lay in each of a series of intervals. So let's say we had a weight in pounds and how it was distributed. In the frequency histogram, we derive the relative frequency histogram, showing the proportion of data in each interval. But you'll recall that by one definition, probability is the relative frequency of an event in the long run. So if we repeat that random experiment many times, the relative frequency histogram of the outcome should come to look very much like the random variable's probability histogram. Illustrate using the random variable x and a mad coin tosser. Tosser begins flipping 2 coins repeatedly, keeping track of the results for a gazillion times. Basically, what we'd see is if we graphed this, comes back to the law of large numbers and the central limit theorem, that this binomial distribution is going to approach the normal distribution, which is kind of the underlying law of all parametric statistics. So we'll talk more about that in the future too. So, example 1. Let's see if I have that one. No, I don't. So basically, how would you read the probability for x equals 23? So you would look at this column and you would say probability that x was to equal 23 would be 10%. Probability of x equals 25 would be 25%. Probability of x equals 26 would be 30%. So the first example is just how do you read a probability relative frequency chart. Example 2, we want to take our values of x in our given probabilities and answer a few questions about them. So that's where we have example 4.2. So first one is, what is the probability that x equals 8? Well, in this case, all we have to do is read the table. It's just 0.2. So the next part B says, what's the probability that x is greater than or equal to 5? So we want to include 5, but we want to include in that probability anything greater than 5. So we can just sum the probabilities for 5, 8, and 9. 70% chance that the probability is greater than or equal to 5. So what's the probability that x is greater than 3? Well, in this case, we don't have a 3, but we wouldn't include it because there's not an equal sign in that inequality or equation. So 4, 5, 8, and 9 are all greater than 3, right? So we can sum those values. And what's the expectation of x? We'll come back to that one because we haven't talked about it yet. So mean and variance of random variables. So we use special terminology and symbols to distinguish between the properties of data sets and probability distributions. So that's the Greek letter mu, which stands for the mean when we're talking about math. So properties of data are called sample properties, while properties of the probability distribution are called model or population properties. So we use the Greek letter mu for the population mean and lowercase sigma for the population standard deviation. And for data or samples, we use the Roman symbols x bar and s, because Romans were short on theory and long on cement and stuff like that. Anyhow, so the sample mean was defined by the equation x bar is equal to 1 over the sample size n, and then you iterate through all of your values and you sum them together. Then you divide by the sample size. That's basically what it says mathematically. So now let's twist that around. So now some of these data points xi may well have equal values. Think of the mad coin tosser. The only available values were 0, 1, and 2, and she made 1,000 tosses. So the value of 0 was taken on 260 times, 1 head came up 517 times, and 2 heads came up 223 times. So as we let x range over all values of x, call n of x the number of data points with the value x, then we can rewrite the formula to include x times the number that it occurred divided by sample size. But now the sample of x divided by the sample size is the relative frequency or the approximate probability, the number that approaches probability of x. So by analogy, we form the expression x is just times the probability of x, and we sum those up, and that will give us the mean of a probability distribution. So definition of the mean of the random variable x is defined as the sum of all the x's, where we multiply x times the probability of x. So basically, it's the center of the histogram. So this is also called the expected value of x, or E of x. Think of it as the sum of the possible values, each weighted by its probability. So it's kind of like a weighted average. So the mad coin tosser's experiment allows us to compare sample mean x bar with our model mean mu. So we had 260 divided by 1,000, so we've got the relative frequency of her actual trials that she accomplished, right? So we had 260, we had 500 or 517 divided by 1,000 or 0.517 and 0.223. So we know that due to the underlying statistical laws, the mean should be 1, right? Because if you think back to the histogram of 0, 1, and 2, 1 was the highest number. And through the trial method, we got 0.963. So this kind of shows the difference between a sample mean and a population mean. We'll talk more about that as well. But you can see, theoretically, we believe the mean of the population is 1, but when we actually take a sample, we get the sample mean is 0.963. So when we get to a chi-squared test towards the end of the class, think back to what you're learning here, because it'll make a little more sense when we do contingency tables. So now let's do the same thing to the variance. Maybe you remember the formula of the variance s squared equals 1 over n minus 1 for the sum of the differences of the each squared. So it almost measures the average squared distance data from the mean as above. This can be rewritten, and basically we can break it down to similar to how we found the variance, and now we just multiply the probability of each of those times the x. So, and then the standard deviation, of course, is the same as before. It's just the square root of the variance. We use the table from the last page to find the variance of the 2-coin toss, for which mu equals 1. So we have probabilities, we have, the mean, or the actual x value minus the mean, which we know was 1. That's the mu. 1 minus 1, that's 0. 2 minus 1. So we can see that if we add those up, we get a variance is equal to 0.5. So sum up the mean and the variance of the population mean and standard deviation are properties we can compute from probability distributions. They are completely analogous to the sample mean and standard deviation computed from sample data. So if you're using Greek letters, it's coming from a population, and if you're using typical X and S, then it's coming from a sample. So for any discrete probability distribution, these are your underlying formulas. So basically we just sum X times its probability. That'll give us the mean. For the variance, we have X squared times its probability minus the mean squared. And then if we take the square root of all that, we can get the standard deviation. Okay, so let's go back and look at, let's go on to here. So we have a set of X values and the probabilities. So based on these formulas, we should be able to find the mean, standard deviation, and variance. So our formula is here. So we want to sum to get the mean is X times its probability, and we sum those together. So we can multiply the value times its probability. Then we can copy that formula down like we did last week with the handle. And it'll give us all of the, intermediate steps. And for the mean, or mu, we just sum those together using the sum function. And we get a population mean of 0.01. So slightly skewed because I would have expected it to be 0, but you can see the probabilities are not perfect. But if we were to get just the mean of these values, it would have been 0. But because the probabilities are kind of a little shifted, then we can see why we would get a different mean value. Okay, so now we know the mean, right? To find the variance, we can use this formula. We sum x squared times p of x minus the mean squared. So we have this. We can use the caret 2. That'll give us the exponent. This will be, x squared. X squared. And we can do that for that. But then we want the probability of x, of that times x squared. So we want probability times the squared value. And we can copy that formula down. So we have that. We want to subtract that value from the mean value squared. So we want mu squared too, right? So if we have e, I have this value. Be a tiny number. So let's see if I can change the numeric. There you go. So, and because we squared it, it can't be negative, which is one advantage of the variance. Okay, so we have that value, and we want to get the variance. Put that here. We want to finish out that formula. So we've computed this and we've computed this. So we just need to subtract them from each other, right? Or I guess I need to sum them together still. So we want the sum to subtract the mean squared. So remember, this column was x squared times p of x, and this was mu squared. So that gives us the variance, and the standard deviation is the easiest because it is just the square root of the variance. I don't remember if it was 3 or 4 decimals, but remember that you can adjust the decimals up here. So it's 4 decimals, 3 decimals, depending on what the software wants when you answer a particular question. All right, so that gives you how to find the mean, variance, and standard deviation for any discrete probability distribution. So our examples so far have been discrete random variables, so their outcomes are a set of isolated or discrete values, like those we saw in Chapter 3, but there are also continuous random variables. So let's imagine a random experiment in which all outcomes have probability 0. That's right, probability x equals 0 for every x. A simple example is a balanced spinning pointer. It can stop anywhere in the circle if x represents the proportion of the total circumference it lands on. The random variable x can take on any value between 0 and 1, so an infinite range of values. So some probabilities are easy to find, like the probability that x falls within a range, for example, probability of 0.25 to 0.75. So that's kind of like looking at a clock, right? Anywhere between 0.25 and 0.75. So anywhere in between here, what's the probability of that happening? Because it's half the circle, so we know the probability of x equals 0.5. So since x can take on any infinite number of values, and all of these values are equally likely, the probability that x is exactly 0.5 or exactly anything is precisely 0, right? Because we really don't know. It could be any value in between 0.25 and 0.75 on this particular scale. So how can we draw a picture of this? By analogy, with the case of discrete probabilities, we try to see continuous probabilities as areas under something. For the spinning pointer, the something looks like this. So basically, it's always 1, anywhere between 0 and 1. So it would be the entire spinner itself. So f of x equals 0 when x is less than 0. F of x equals 1, 0 is between, or when x is between 0 and 1. And if f of x is equals 0 when x is greater than 1. The probability that the pointer points anywhere between A and B is precisely the area of the shaded region under the curve between A and B. In this case, B minus A. Probability of an exact outcome, however, is the area over a point which is 0 and not the total area under the curve is exactly 1. So the same picture describes the random number generator found on most computers, in particular Excel. If you're using the rand function, which I can show you in a second, you'll probably use that in an operations management class, but maybe not so much here. And some calculators. So press the button, out pops a number between 0 and 1, and all the numbers are equally likely, just as with the spinning pointer. But sadly, they aren't truly random. They're produced by some algorithm. So they're called pseudo-random numbers because it's actually, a computer can't really generate a random number. It can pretend to. So in general, the probability density won't be so simple. And computing the areas can be far from trivial. So this is the integration of f of x equals d of x, but we're not going to go into the calculus level. We're not theoretical statisticians right now. So just know that when we're finding mathematically the means of a continuous distribution, we're going to use some calculus shortcuts without having to actually do the calculus. So as a sum like something, the integral serves to define the mean and variance of a continuous random variable. So the mean is from negative infinity to infinity of x of x d of x. But by analogy, with the discrete formula, we can see it's x times the probability of x. Same thing with the variance. Although it may not be obvious from the formulas, these definitions of mean and variance are entirely consistent with their role as center and average spread of the probabilities given by the density of some particular function. So the picture to keep in mind is if we had a normal curve with some mean and we had one standard deviation in either direction, the mean minus one standard deviation or the mean plus one standard deviation. For example, look at a fair coin toss. Let x equals 1 if the coin comes up heads and 0 if it comes up tails. So a very simple coin toss, binomial experiment. Right now you should be able to find the mean. So the expectation of x equals 0 times probability of 0 equals 1 times probability of 1. So 0 plus 0.5, that's how we get 0.5, or a 50-50 chance. And the variance is the outcome minus the mean squared times the probability plus a particular outcome minus the mean squared times its probability. So, the variance is 0.25. Standard deviation would be the square root of that. So, we have a special distribution that I've been mentioning all along called the binomial distribution. So we let P equal the probability of success and Q equal the probability of failure, so 1 minus P, and N equals the number of trials, and R equals the number of success in N trials. So to find that probability of R successes for N trials is given by the following general formula. It's a big long formula. But how can we calculate this out? For an example, if x is a binomial random variable, compute the probability of x given that n equals 4, x equals 1, p equals 0.6. So we have our formula. We want to find probability from a binomial distribution. So we have n trials, right? So we'll go back up. N number of trials equals 4. the number of successes is 1. The probability of a success is 0.6. So for this formula, we need Q, and Q is probability of failure, or 1 minus P. So it's just equal to 1 minus probability. Now to find the probability of X, given the information, we just need to implement our formula. So in factorial, in fact, r fact, okay, this will be 1. Then we have n minus r. Factorial of n r. Then we have p raised to r equals p raised to our number of successes. And we have q raised to so we're calculated out q here. So we have q, and we're going to raise that to n minus r. Now, to find this probability that we're interested in, we're going to carefully put this all together. Let's start with the parentheses. We have n factorial divided by r factorial times n, oops, I want this one, n minus r factorial. So this times this. I want to keep that fraction together, and I want to multiply p to the r times q to the n minus r. That will give us our probability. And you may need to adjust to 3 decimal points. I don't remember what the Pearson wants. But what we've done is created a little calculator that all you have to do is, if you're given the number of trials, it'll auto-update. If you're given the number of successes, it'll update. If the probability changes. So now you've created your own little calculator that will give you the missing values or find a probability of X given a binomial distribution. Okay, so the cool thing about binomial distributions is they have some very simple ways to find the mean and the variance. So the mean is just sample size times probability, and the variance is the sample size times the probability times the complement of a probability. So we have another example. Given a binomial random variable, calculate the mean, variance, and standard deviations for a set of numbers. So if we have n equals 30 and p equals 0.5, we know that q, well, I guess I'm going to put this over here, 30, 0.5, q is going to be 1 minus p, which will be, and we want to find the mean. Well, the mean is just n times p, so n 30 times probability is 15. Variance is n times p times q. And then the standard deviation is just the square root of the variance. now. Likewise, we've created a small calculator, and you can adjust these values, and using these Excel formulas that we put in, you can adjust how to calculate that out. I believe that is the end of chapter 3 and 4. So still a lot of definitions and underlying theory, but hopefully that will help you understand future material.